Hello students, welcome back to PH107 Quantum Physics and Application. Today I am going to discuss harmonic oscillator quantum mechanically, but before we go and discuss how interesting results we are going to obtain for a harmonic oscillator within the quantum mechanical treatment, let us revise what we know so far about harmonic oscillator in classical physics point of view. So in classical mechanics, a simple harmonic oscillator can be expressed in this following fashion. So here is a spring with mass m, and the equilibrium distance of this mass from this rigid end is x0, and suppose you exert a force to this mass downward, then you make a displacement, and once this displacement is met to this particular spring mass system, this system or this harmonic oscillator system follow this following equation, where this is a force m is into acceleration, or the second derivative of your position with respect to time, and the right hand side is restoring force, because there will be a restoring force opposite to the direction of the displacement, where k is your spring constant, and now if you look the solution of this equation, what we have done in the past, that the solution of this standard equation is written in this following fashion, where the displacement is written as a times sine omega t plus phi, where a is the amplitude of this oscillation of your harmonic oscillator, and omega is the frequency of your oscillation, and phi is the phase. Now once you know the displacement, you can also obtain the expression for the velocity, which is the first derivative of this x with respect to t. Now the solution of these harmonic oscillator in a classical physics or this particular differential equation is oscillatory in nature, with an angular frequency or circular frequency omega, where omega is your square root of k over m. Once you know these solutions, let's write down the expression of the total energy. So the total energy is kinetic energy half mv square plus potential energy half kx square, where k is your spring constant as we have discussed in the previous slide. So let's substitute the expression of v from here and the x from here. So we can write down half m. Now this v is your omega square a square cosine square omega t plus phi, plus half k, and x is your a square sine square omega t plus phi. Now from the previous slide, I know what is the value of my k. K is your omega is your square root of k over m. So my k is your m omega square. So that's what I have rewritten here. And now I can take out cosine square omega t plus phi plus sine square omega t plus phi, which will give me identity. So at the end, the total energy is obtained as half m omega square a square. Now I can rearrange this total energy and the frequency and the amplitude of your displacement in this following way, so that I can obtain what is my displacement in terms of the energy. So this can be written as plus minus, because here is square and you are taking the square root, so this will be plus minus square root of 2e over m omega square, and I can rephrase the whole thing in terms of the spring constant. Remember the value of the spring constant k, here I have written m omega square, so I can again resubstitute the value of m omega square. So this is the displacement I have obtained in terms of the energy and spring constant, and these are I can now deduce, or I can express the notion of what is known as classical turning point. So what is the classical turning point? When the total energy is equal to the potential energy, okay, and at that point now I can call as it the classical turning point. So let's write E is equal to half k square. This is the total energy, and this is my potential energy, and now I can write down my x as equal to plus minus 2e over k. So you can see that now your A is equivalent to the classical turning point. So this is the what we have seen in the previous slide, that your classical turning point is the place when your total energy becomes equal to the potential energy and there is no kinetic energy term left, and under these circumstances your displacement or the maximum displacement is written as square root of 2 EOR K. So let's now look how this classical turning point looks like and what are the consequences. So here is your harmonic oscillator potential. So this is the origin and this is the displacement axis and this is the total energy, and so the total energy is here. So at this point when we have this equilibrium at this one, your um, spring mass system is in the equilibrium at the zero displacement because the displacement is zero at this point. Okay, and now when it reaches to this one, it means that your displacement reaches to the maximum, and this is the one at which you have a classical turning point. That's what we have expressed by this following expression. And now by using the force acting on this harmonic oscillator system or spring mass system, we can deduce the form of the potential. So now after learning or after recapping the notion of classical harmonic oscillator, let's move on what we are going to learn about the quantum mechanically. But before that, let me try to motivate why we are so much interested to learn harmonic oscillator quantum mechanically. So the first motivation comes from the following region. So let's draw any arbitrary potential. So this is any arbitrary potential along one dimension V of x, and this is the global minimum disharmonic potential at position x0. The value of this potential is V0, and this is the some finite value E. Okay. So now what I'm allowed to do, I'm allowed to express this total potential V of x in this vicinity of this minimum V0 in this using the Taylor series expansion. So I'm expanding my total potential in this vicinity of the equilibrium or the minimum using this Taylor series. So the first term is your V0. The second term is your first derivative of your potential with respect to the position at this position x0 times x minus x0, plus the second term is the second derivative, and so on and so forth. So let's rewrite this expression in the next slide. So this is what we have written. Now we know that at this position at which we have expanded this potential in this minimum in the position of minimum potential or the equilibrium is 0. So the force acting on this particle is 0. So this is 0, and we know that d2v over dx2, because this is a stable minima, is a positive quantity. So let me rename as k to this particular value of the double derivative of this potential with respect to the position. So now I can re-express my this Taylor series expansion into this following form, and I have ignored the higher order term in this series expansion. So this is what I have obtained. Now my position of the minima in the potential and its value is completely arbitrary. So what I can do, I can shift the position to the origin in such a way that my V0 becomes 0 at x is equal to 0, in such a way that I have obtained my total potential, which was arbitrary in shape, and when I perform the Taylor series expansion in the vicinity of the global minima, I have rewritten the total potential as harmonic oscillator potential, or half kx square, where k is some constant. Here it doesn't matter what is this one, and this mimic the shape of the harmonic oscillator potential what we have seen in the earlier slide. So this is what I have said, that this is your arbitrary potential. So if you are in this minimum at x0 is equal to 0 and v0 is equal to 0, so I have shifted the origin, and if you are just a small displacement away from this equilibrium, so you could see that I am allowed to represent this arbitrary shape potential for which I don't know the mathematical form in the form of the harmonic oscillator potential, and you can see this black curve matches quite well with the red curve up to a certain extent away from this equilibrium position 0 0. Okay, so that's what I have tried to explain, or I have to emphasize you that for a small displacement or a small excursion of the particle away from this minimum position 0 0, the arbitrary potential can be approximated to be a simple allowance. So this is the one important motivation to learn harmonic oscillator potential. Quantum mechanically, the other motivation comes from the fact that the atoms in any form of matter, whether it's molecules or solids, in the vicinity of the equilibrium, the interaction potential can be approximated as a harmonic oscillator potential. So you could see that here is my diatomic molecule where the two atoms, two different kind of atoms, are attached by a bond, and this bond can be mimicked as a spring mass system. And you could see that when this is the true potential, which is shown in the red color, and this is the approximated potential shown in the blue color, and you could see that at the equilibrium this potential matches quite well in this vicinity of this equilibrium. And this approximation or this treatment of replacing the true potential by harmonic oscillator potential is not only applicable to the diatomic molecule. If I go to the triatomic molecule, this I can also do the same. And if I go beyond the molecular physics and go to the solid, so all the here is representation of your periodic arrangement of atoms within this solid, and you could see that these are the positively charged ions, and these ions are attached with each other by this spring, and the whole system can be mimicked using spring mass system. Just as a side remark, that the true potential of a molecule is represented as a Morse potential, which is beyond the topic of your study. So let's explore the quantum mechanical behavior of a particle subjected to a harmonic oscillator potential. So let's write down the time independent Schrodinger equation, and by now you are familiar with how to write down immediately the time independent Schrodinger equation for a given potential. So this is the kinetic energy operator, minus h cross square over 2m d2 over dx2, as we are still limited ourselves to the one-dimensional system, and this is the form of the potential that we have seen just now, half kx square. So this is the kinetic energy, this is the potential energy term, and this is the kinetic energy operator, this is the potential energy operator, and the total term written in this bracket is the Hamiltonian. So this is your total energy in some sense is this is the total Hamiltonian times your wave function is equal to total energy times psi of x. Now I can rearrange these terms, and I can introduce the value of my k as square root of k in terms of the omega and m. So I can rewrite the above equation as half m omega square x square times psi of x. Okay, so now what I can do, I can only try to express my double derivative of my this operator d2 over dx2 times psi is equal to rest of the thing. So what I did, I took this quantity to the right hand side, and then I have multiplied by this whole quantity in the right hand side. So the total equation is recasted in this following fashion, that d2 psi over dx2 is equal to 2m divided by h cross square times half m omega square x square minus e times psi. You will appreciate why I have transformed in the following fashion. So now the task is left to know what is the value of psi and what is the value of e. Solving this equation in a complete sense is beyond the scope of this course. It is one of the difficult problem which requires the knowledge of a special function. I will write down the complete solution just for your knowledge at the end of this lecture. So let's focus on, in a approximated way, what could be the possible solution of this equation for a ground state. So what will be the psi or the wave function for the ground state, and then we will try to deduce what will be the corresponding energy for the ground state. Okay, so from our previous knowledge of whether we talk about the scattering problem or whether we talk about particle in an infinite box or finite box or semi-finite box, we have used either exponential form of the wave function or the trigonometric form of the wave function, which are not going to be applicable here because your potential term has x square form, which was not the case in the earlier situations where your potential was not of the form of this one. So what we could do, so these, either the exponential form of the wave function or the trigonometric form of the wave function, are not going to be applicable for this present problem. So let's use our common knowledge or the learned knowledge to guess the form of the wave functions for the ground state. Uh, so the ground state wave function must possess the following attributes. So the wave function should be antisymmetric about the midpoint of the potential, because your potential is symmetric at x is equal to 0. So the wave function should be symmetric. Also, the wave function must be nodeless but approaches to 0 as we reach to x is equal to plus minus infinite, or mod of x becomes a very large value. So, okay. So based on these two criteria, so what the first condition imposes that your psi, your wave function, be some sort of the form of x square. Okay. Now the function must have no zeros, so it has to be nodeless other than at infinity to meet the criteria of the nodeless requirement imposed by the condition 2. So by using these two criteria or conditions, the simplest choice that the simplest form of the wave function that fulfills both the requirements have to be the Gaussian form. Okay, so this is the equation that we have taken from the previous slide, and let's guess the functional form for this psi is in the form of the Gaussian. So in the previous lecture we have written the Gaussian forms when we were discussing about the uh, probability and the average value and all these things. So we have done a detailed discussion about the Gaussian form of a function. So here is your C naught is some constant e to the power minus alpha x square, where alpha is another constant. And now let's try to substitute this following form of psi to the left hand side of this equation, which is the double derivative of your psi with respect to x. So when we will perform the first derivative, what we will get? We will get C0 times minus alpha, okay, times 2 of x into 2 e to the power minus alpha x square, and then we have to perform another uh, time derivative, and once you perform the derivative you are going to obtain this following form. So the first term will be your 4 alpha square x square, and the second term will be minus 2 alpha, and here I have taken the Gaussian form outside from both the term. So this I can again replace by psi of x, because that is my trial wave function. So now I have the expression for the left hand side, and this is my right hand side. Right hand side also has a two term. So now I can equate term by term. So the first equating will give me 4 alpha square x square is equal to 2 m h cross square times half m m omega square x square. X square x square cancel out, so the 4 alpha square is left with this quantity. Or if I rearrange everything, I have obtained alpha is equal to m omega over 2h cross square, and in the right hand side I am left with the 2 alpha is equal to e times this quantity, and now I know the value of alpha, so I can substitute these values, and now I have obtained e is equal to half h cross omega. Now you may recognize that the ground state energy of a harmonic oscillator is half h cross omega. This is the same value we have obtained using the uncertainty principle, and this is what is known as a 0-point energy. Okay, so this is the functional form of your, or the ground state form of your wave function for harmonic oscillator. Now I have substituted the value of alpha from my previous slide. Still I have kept C0 as a constant, and it's your first homework to determine the value of C0 by imposing the condition of the normalization of this wave function such that mod of psi square, when you integrate over entire space, it has to be unity. By this you can obtain the value of your C0. So let me plot the wave function. So this is my wave function psi of 0 for the ground state, and this is the probability of finding the wave function, probability of finding the particle in the ground state, which is the mod psi 0 square. Okay, now let me write down the complete wave function or the generalized wave function for a harmonic oscillator in one dimension. So this is the general solution. So this is n stand for any nth state, which is 1 over square root of 2 to the power n times factorial n times this prefactor e to the power minus m omega x square over 2h cross. So this is the quantity or this structure that you have obtained, and it is multiplied by this special function h of n, in this parenthesis square root of m omega over h cross times x, and this special function is known as Hermite polynomials, and this has this following form. So knowledge of these special functions are beyond the scope of this course. That's why you are not able to find the general solution with this limited knowledge, but just for the completeness I have written down the general form of this wave function. Now let me plot, once I know the general form of my wave function. So here is my psi 0, which I have plotted this in the form of the Gaussian, and this is the first one. It has one node, as you have also seen in the case of particle in a box. As you increase the value of n, you start seeing that they have nodes in between this thing, and these are the probabilities. Now one of the important observation you could make it immediately, that the wave function extend beyond the beyond the region of your potential, and that what is known as a classically forbidden region in the context of the quantum mechanics. So the probability of finding the particle quantum mechanically is non-zero beyond this forbidden region. That's what you have seen in the particle in a box, or in the case of the tunneling. And this is the generalized expression of your total energy, which is n plus half h cross omega, where n start from 0, not from 1, and the g for the first value is known as the what you say, the 0 point energy. So here is your second in video quiz. So we have seen that this is your ground state wave function for a harmonic oscillator, where alpha has this m omega over 2h cross square. So now you have to show that the product of the delta x delta p, which is the uncertainty in position and momentum, is the minimum for the ground state wave function of a harmonic oscillator, which has this Gaussian form of the wave function, which is s cross by 2, where delta x is your uncertainty written in this following form, and delta p is written there. Before I end today's lecture, let me provide the recommended reading for this particular topic. So if you are interested to know more about quantum oscillator, please go to section 6.6 of this book, Modern Physics by Survey and co-authors. Thank you very much, and see you in the next lecture.